Okay. Good afternoon, everybody. Okay, you have a choice between me and lunch. You guys probably did not win. Okay, so my name is Graham Wilson. I'm responsible for product within Akeana, and I will give you a short overview of Akeana products and why we are focused on breaking performance barriers. So let's start off with a little bit about the company. So the company, it's a young company, but with a very mature, experienced team. We've got a very strong, proven legacy in the development of high-performance processors within the team. And our key drive, our key focus is we are an IP company. We provide IP, and we really want to enable our customers to succeed, our SoC customers to succeed by providing them with the highest performance processor system IP. So when we look at the processor system, I just want to give you an overview of the products that we offer. And these are off-the-shelf products that are available today. You could take them away today and put them in your SoC. We offer a broad range, the same equivalent range of ARM products. So starting with the Akeana 100 series, it's the equivalent of an ARM Cortex-M, very small, very energy efficient. Then the Akeana 1000, which is more consumer-orientated, more data processing, optimum performance per watt per millimeter squared. And then the Akeana 5000 series, which is really our flagship product lineup. We have the highest performance, out of order, widest instruction issue to get the real top-end computation capability. And when we look at that, I've reused a slide from a previous RISC-V summit with the dots in blue of SoC implementations as well as other IP providers. And then I've plotted the Akeana 5000, which is 5100, 5200, and 5300. And as you can see, the Akeana 5000 series really leads in terms of performance. And these performance numbers are spec in per gigahertz in a single-threaded implementation. I want to talk a little bit about what we're seeing that's evolving and a few of the trends that are occurring. And when we talk to our customers and find out their computation needs, we're seeing a trend for something that's a little bit, for me, is a little bit surprising, but is the drive towards multi-threading. Here's a great example. NVIDIA recently announced in their next generation of CPU compute array, silicon, Vera, that they moved away from taking the traditional off-the-shelf CPU core products and moved to much more customization of those CPU cores in order to gain the next generation performance. And in order to achieve that, they moved to multi-threading. And so in a way, they've kind of planted the flag for the simultaneous multi-threading. And Akeana, given our legacy, given our background and development of, say, for example, ThunderX, which is a multi-threaded architecture processor, Akeana, we've implemented multi-threading in our 1000 and 5000. So really, Akeana is a leader in terms of providing processor IP, processor system IP for multi-core, multi-threaded, coherent systems. So if we take a look at some of the numbers around that we're seeing the performance boost for multi-threaded implementations, and this is based around our out-of-order as well as in-order implementations in the Akeana cores. So, for example, traditional benchmarks like SpecInt, when we ran that on a single 2-thread and 4-thread, we get a sizable performance improvement, almost 30% improvement on the SpecInt scores. But when we go to computation, where a lot of it is data computation and you're waiting on data availability, there may be memory bottlenecks and so forth, then you get real improvement from multi-threading. And that's almost 2.25x performance improvement from multi-threading. And we see that more and more in terms of the customer engagements or requests for multi-threading, as well as there is the other option that you have multiple threads for execution and other threads that may be doing system management, hardware accelerator management, and synchronization tasks. So another area for performance for Akeana is in the ability of the data computation. So we implement our cores with vector extension. They can actually go up to 4K vector length. And we did an AI core implementation where we took a 2K vector length. Coupled with this, we also implemented custom instruction acceleration for AI nonlinear functions. Things like sigmoid, exponential functions, GELU, we accelerate those with custom instructions, giving much higher data computation capability. So when we then look at some of these activation functions and at the higher level, for example, softmax, the acceleration that is needed in the areas for softmax, we've seen there's three main areas: the wide vector capability, the ability to vectorize the data and pump it through the vector ALU as quickly as possible, the custom instructions for nonlinear functions. Also, data movement is a key part because there's a lot of data management for soft matrix and movement around. So our data movement engines that we have as part of our solution greatly accelerates that. So we see very high performance from the softmax. Another area for the performance is through scalability. So especially with some of the high-end cores where you want to run maybe single thread or just an OS and various different applications on a computer array farm, performance through scalability is a key point. And so we offer a single coherent cluster where you can have up to 8 cores with a shared memory, all fully coherent. This can be cores, it can be hardware accelerators, AI gem engines. We can then leverage that and drop that into a coherent mesh array that then you can build up in a 2-dimensional mesh array that you can build up potentially up to thousands of cores. The specification will allow. We've built it up to 128 cores, 256 cores. And we provide all of the hardware blocks that allows you to build these like Lego blocks and then hook up. And we've built these systems for customers and delivered it as a GDS2. And then also the final part in terms of optimization of performance is data movement. So I talked about we have a cluster where multiple compute arrays and hardware blocks and gem engines can sit and share across a shared cache. For AI computation, we also have a shared AI SRAM banked memory where the cores and the accelerators and the hardware blocks all operate in parallel, can take data in parallel from the different banks within that shared memory, and they also have multiple interfaces out of this cluster for weight data and different types of AI static computation data. So in summary, for Akeana, the thing to remember, Akeana as always is about performance in terms of the CPU compute, the 25 spec int, and then the multi-threaded support capability. Performance in data compute, the very wide vector length, the acceleration, nonlinear custom instructions. Performance from scalable multi-core, the cluster, and also the 2D mesh scalability. And then finally, the data movement. Parallel operations, parallel paths, and data movement engines. Okay, thank you very much.